to begin our discussion in Chapter 10, we need to remember some of those rules of exponents that we learned a long time ago. Namely, if you have something to the fifth power, you've multiplied it by itself 5 times. If you have something to the negative fifth power, you have then put that in the denominator and multiplied it 5 times. Anything to the 0 power is equal to 1. So now we have this idea of some number to the 1/2 power, b to the 1/2 power, or you can just say b to the 1/2. If you use the law of exponents and you raise b to the 1/2 power and you square it, you multiply your two exponents together, which gives you b to the first, which is b. So since the square of b to the 1/2 is b to the 1/2 is the same as the square root. You'll see this also if you take something to the 1/3 power, you actually get the cube root of b. Sometimes we see things like this where it's b to the 2/3 power. So if we use the power of a power rule, b to the 2/3 is like saying b to the 1/3 squared, or b squared to the 1/3 power. Let's evaluate a few of these examples. If we have 81 to the 3/2 power, that's the same as saying 81 to the 1/2 power cubed. And 81 to the 1/2 is like the square root of 81 cubed. Well, the square root of 81 is 9. And 9 cubed is 729. The next one I have 9 to the 1.5 power. Alright, well that's the same as 9 to the 3/2, which would be 9 to the 1/2 cubed. Amazingly enough, it's the same idea, regardless if you write it like this or like this. 9 to the 1/2 would be the square root of 9 cubed. Square root of 9 is 3, and 3 cubed is 27. For the next one, we have the 1 over the cube root of 81 to the negative 3/4 power. Now this really isn't a very pretty problem, but we can always rewrite it. We can say that we want to take 81 to the negative 1/3 and raise that to the negative 3/4. Now, when I use the power of a power rule, I multiply these two exponents together, and that gives me 81 to the 1/4 power. 81 to the 1/4 power is like saying 81 to the 1/2 to the 1/2. Well, why would I do that? I know what 81 to the 1/2 is. It's 9. And I'm going to raise that to the 1/2 power, which will give me 3. And the final one on this page, we've got the square root of a third times the cube root of 9. The way I'm going to approach this problem is I want to try and get the same power of everything. So what I'll do is I'll make this 1 over the square root of 3, and I'm going to make this the cube root of 3 squared. So the 1 over cube root of 3 is 3 to the negative 1/2 power. And then the cube root of 3 squared is 3 to the 2/3 power. And now, because I have the same base, and I'm multiplying, remember those rules, you can't forget them, I can add my two exponents. Obviously, that means you have to remember how to add fractions. But this becomes 3 to the negative 3/6 times 3 to the 4/6, which gives us 3 to the 1/6 power. Or we could call that the 6th root of 3. So here we've got a product that we want to write in exponential form and in simplest radical form. So 9, or cube root of 9, is just like saying the cube root of 3 squared, which we did this one already, so that's 3 to the 2/3. Square root of 3 is 3 to the 1/2. So in exponential form, that's not going to erase. Okay, sorry, I was trying to erase that because it didn't write correctly. 3 to the 2/3 times 3 to the 1/2, similar as the last problem. We've got 3 to the 4/6 times 3 to the 3/6, which is 3 to the 7/6. If we're going to write this in simplest radical form, we would have the 6th root of 3 to the 7th. That's really the 6th root of 3 to the 6th times 3. Why do I want to do that? Well, there are 6 3's here that can come out of this radical, so I'm really looking at 3 times the 6th root of 3. Here we've got some equations that we're going to solve. Simple enough. The first step is to divide by 6 on both sides. So we have x to the 2/3 is equal to 9. Now what I need to do is undo this exponent. So when I undo the exponent, that means I'm going to multiply, or not multiply, I'm going to raise this to the power of the reciprocal of the exponent on both sides. This cancels and we get x, and then 9 to the 3/2 power would be the square root of 9, which is 3, cubed, which is 27. Next problem, very similar. First thing I need to do is add 3 to both sides. I have t minus 4 to the 2/5 is equal to 4. Now when you do order of operations, you have to work from the inside out, and the next thing I have to do is, when you do order of operations and you're solving, you work from the outside in. It means you do your order of operations backwards. So I have to get rid of this exponent before I can do anything else, which means I will raise both sides of this equation to the 5/2, which cancels this, and I get 4 to the 5/2 power. So 4 to the 5/2, that means 4 to the 1/2, which is 2, and then you raise that to the 5th power, which is 32. So I have t minus 4 is 32. Then I add 4 to both sides, and I find that t is equal to 36. The last section looked at rational exponents. Now we're going to look at exponents that are real numbers, but that are not necessarily rational. Think about this equation, y equals 2 to the power of x. I can put in integers. I can put in fractions, 0, whole numbers. If I plot these points, here's the graph that I get. But points actually exist between these numbers. Those are the irrational numbers, like the square root of 3. So in order to make this graph continuous, we have to be allowed to enter things like square root of 3 into the equation so that 2 to the power of square root of 3 does show up as a point on this graph. These are called exponential functions because our x is in the exponent. So I always like to let you hear me say that. An exponential function has an x in the exponent. One-to-one functions are also very important. It's a function where any y value is the result of any one x value, meaning that you can draw a horizontal line through the graph and it only intersects one time. Exponential equation is an equation where the variable is an exponent, pretty similar to an exponential function. The big difference here is that the base cannot be equal to 1 because 1 to any power is just 1. So if you consider this exponential function for values where b is greater than 1, the graph increases, right? This is what you see here. If this number is between 0 and 1, it's going to decrease. What you need to notice is that we do not have a base that's negative. The reason that we don't have a base that's negative is because it will fluctuate and we'll have a lot of asymptotes. Because for a positive exponent, it'll be here, and for a negative exponent, it'll be here. So your graph will be jumping. So in general, we have, for exponential functions, our y-intercept is 1, because b to the 0 power is equal to 1, and we have the x-axis as an asymptote. Obviously, these things can change when you start adding, adding a constant to each function, but in general, this is true. Now, the great thing is that the rules of exponents still apply. So we've got a base of 2, and we're multiplying, which means that we can add these two exponents together. So we get 2 to the 4 minus square root of 5 plus 1 plus the square root of 5. 4 plus 1 is 5. Negative square root of 5 plus square root of 5 is 0. So this is 2 to the 5th, which is 32. Next problem, we're taking power raised to a power, which means that we can multiply our two exponents together. So we have 5 to the power of 2 square root of 3 times the square root of 3. Square root of 3 times square root of 3 is 3. 3 times 2 is 6. So this is 5 to the 6th power. I don't expect you to memorize that, but you put it in your calculator. You get 15,625. Last equation, we're dividing. We have the same base, which means that we can subtract our two exponents. So we have 3 to the 2 plus square root of 7 minus 2 minus the square root of 7. Notice that I put this in parentheses, and I will have to distribute this negative. So that becomes 3 to the 2 minus 2 plus square root of 7 plus square root of 7. 2 minus 2 is 0. I get 3 to the power of 2 times the square root of 7. And I can leave my answer just like that. Now, when I'm dealing with exponential equations, and I need to solve them for x, the first thing that we're going to do is get each side of the equation as some power with the same base. So if you look at this first one, I've got a base of 4 and a base of 2. Well, I know I can rewrite 4 as 2 squared to the 2x power. And I know that I can rewrite 1/2 as 2 to the negative 1 to the power of 1 minus 2x. So the next thing that I can do is simplify that, right? I can multiply these and multiply these together. So that gives me 2 to the 4x power. And this is 2 to the 2x minus 1 power, right? Because I had to distribute negative 1 times 1, negative 1 times negative 2x. The next step, set the exponents equal and solve. Well, now I have the same base, which means that these exponents need to be equal to each other. So 4x has to equal 2x minus 1. That means 2x is equal to negative 1, so x is negative 1/2. Let's try another one. So I have 5 to the 3x power, 1/25, right? 25 I know is 5 squared, so 1/25 has to be 5 to the negative 2. To the x minus 1. Then I'll multiply these together. And and that becomes 2 minus 2x. Now, since my bases are the same, these two exponents have to be equal. So I get that 3x is equal to 2 minus 2x. And x is equal to 2/5. This last section that we're covering is over composition and inverses. So first we start with composition, and we think about these functions, right? F of x and g of x. Remember, this does not mean f times x or g times x. It's the function of x. So we've got x squared and we've got 2x. What we can do is combine them to produce a new function where you have f of g of x, which is how you read this. What you have to do is work from the inside to the outside. So if I'm going to take f of g of x, let's pick a number like 3. I'm going to start with the inside, and I'll say, okay, well, I would need f of 2 times 3, which is 6. Now, so what I did is I plugged 3 in here. So now I'm going to plug 6 into this one. F of 6 is 6 squared, which is 36. Whenever we have a function like this, we call it the composite. And this operation is called the composition. So we can take f of g of a number, we can also take g of f of a number, and we can apply this to variables. So if we have f of g of x, what that means is we're going to take f of 2x, which means we'll take 2x and square it. Let's do a couple of examples. F of g of 3. So I'm going to take f of 3 plus 5. Oops. Let's do that a little bit better. Which means I'm going to take f of 8. And f is square root of 2x. So f of g of 3 is 4. Let's try g of f of 3. So I'm going to take g of the square root of 2 times 3, which means I'll be taking g of the square root of 6, which means I'll be doing the square root of 6 plus 5. So notice that f of g of x and g of f of x, they do not give you the same number. I can generalize this information. F of g of x means I'm going to take f of x plus 5, which means the square root of 2 times x plus 5, which is the square root of 2x plus 10. G of f of x means I'll take g of the square root of 2x, which is the square root of 2x plus 5. Again, notice that these are not equal. Inverse functions are functions that undo each other. And the way that you find if two functions are inverses is you take the composition, either f of g or g of f. And if your answer is x, when you do that composition, then the functions are inverses of each other. Some things to pay attention to. I've got my function here, f, and here's its inverse. What I want you to pay attention to is this black line. Functions and their inverses are symmetric over the line y equals x. Also notice, I have a point -2, 1. On the inverse, my point is 1, -2. I have this point -3, 1/2. Here, it's 1/2, -3. Point AB, point BA. Notice that the x and y values switch place. The notation looks like this, and you read it f inverse. please, please, please understand that this is not an exponent. It is the inverse of a function. Not every function has an inverse. Remember those one-to-one functions I told you about with that horizontal line test? This function, which is x squared, does not have an inverse because it does not pass the horizontal line test. Now I can graph it because I can undo this, but here's the graph of the inverse. And if you notice that this is not a function because it doesn't pass a vertical line test. Vertical line test, function, horizontal line test has an inverse. Okay, last set of examples. We're going to show that these two are inverses. So what I'm going to do is I'm going to take f of g of x. So I'll do f of 3x plus 3. So that means I'm going to put 3x plus 3 in place of x. So I'll take 1/3 times 3x plus 3 minus 1. That's f of g of x. So 1/3, when I distribute this 1/3, that's going to be simple enough. 1/3 times 3x is x. 1/3 times 3 is 1. I get x. So f of g of x is equal to x. So these are inverses. The next question asks, if g of x is equal to the absolute value of x, does g have an inverse? Now remember, it has an inverse if graphically it passes a horizontal line test. Well, what you should remember about the graphs of absolute values is that they look like this. Does that pass a horizontal line test? No, it does not. So this does not have an inverse because it does not pass a horizontal line test. Now, the most important thing is being able to find the inverse of a function. So I'm given this function f of x is equal to the square root of the quantity x plus 1, and I need to find the inverse. So what you need to do, change f of x into y. Now remember what I showed you on those graphs, how x's and y's switch places? That's what you'll do. Now, solve for y. What would you do? How do you undo this square root? You square it. So you're left with x squared is equal to y plus 1. And then you subtract 1. So the inverse is x squared minus 1.